Swayam Prabha. Digital India. Educated India.
Namaskar. So, in this class we will discuss about the transfer function, and we will see what we discussed in our previous class first, and then we will proceed to transfer function. So, in the last class we were discussing about the circuit analysis using Laplace transform, and we discussed that the circuit analysis using Laplace transform involves these three steps. First step was the transformation of the circuit from time domain into S domain, and then we solve the circuit using any circuit analysis technique, that may be nodal analysis or mesh analysis, source transformation, superposition, and so on. And then finally, what the result we get, that is in S domain. So, we will take the inverse Laplace transform to find the solution in time domain. Now, while doing the circuit analysis using Laplace transform, how we will transform the circuit elements from time domain to S domain. For resistor, there will not be any change. So, value of R in time domain will remain R in S domain also. So, V t is equal to I t into R, that is the Ohm's law, will become V s is equal to R into I s in S domain. The changes would be there in case of inductor and capacitor, because these are the energy storage elements. So, we will have some initial conditions, like in case of inductor we may have initial current I naught. So, we discussed that we can transform those time domain circuit for inductor into S domain. So, this was for voltage, where you see this would be applied in case of Kirchhoff voltage law. Similarly, for current you will have the circuit as shown in the figure. This is what we discussed in the previous class, that the direction of the current source, that is the fictitious current source which we added because of the initial condition of current I naught flowing through the inductor. So, the direction is conforming to the plus sign here, and similarly for here the initial condition in terms of current will be minus of L I naught, that is why it is having the opposite sign for voltage. So, this we discussed in the previous class. Similarly, for capacitor also we discussed that we will have the two equations, one for voltage and another for current. For voltage, if you transform the time domain circuit into S domain, this will be as shown in the figure, where V naught by S would be the initial condition, that means the voltage across capacitor at time t is equal to 0. Similarly, the equivalent current source will also be represented when you are finding out the current flowing through the capacitor in S domain, and C V naught, that is the virtual current source, will have the direction of current opposite to the flowing from the voltage source, that is V s. So, this is because you have the negative sign here. So, these things we discussed in our previous class, and then we utilized these equivalent circuits, and we created the circuit in S domain and solved it. Now, let us proceed forward with the transfer function. So, what is transfer function? Transfer function is a key concept in signal processing, because it indicates how a signal is processed as it passes through a network. So, basically you can say that this is a fitting tool for finding the network response, determining or designing for the network stability and network synthesis. So, we will discuss the application of the transfer function when we will discuss the network stability and network synthesis concepts later in the course. Now, the transfer function of the network describes how the output behaves with respect to a particular input, and how it will have we will see in the next slide. And it specifies the transfer from input to the output in S domain, assuming no initial energy. So, how we will define the transfer function? Transfer function we generally call it as Hs, which is nothing but the ratio of output response to the input excitation with all initial conditions as 0. So, you can represent the transfer function Hs is nothing but Ys is nothing but output response divided by the input excitation, that is Xs. So, the transfer function depends on what we define as input and output. Now, since the input and output can either current or voltage at any place in the circuit, so therefore, we can have 4 possibilities in case of the transfer function. First is Hs in terms of voltage gain, where you correlate the output voltage, that is output response of the circuit in terms of voltage divided by input excitation given in the form of voltage. Next is current gain, that is again the transfer function which correlates the output current with input current. So, I naught S is the output current of the circuit divided by this Is, that is input current for the circuit. Now, next transfer function can be a impedance, where output is in the form of voltage while input is in the form of current. Similarly, it can be admittance also, where output is in the form of current and input is in the form of voltage. So, then it will become Is divided by Vs. So, in that way we can say a particular circuit can have many transfer functions. Now, if you see the first two transfer functions, that is voltage gain and the current gain, these are dimensionless because the output and input quantities are same. So, for these two cases the transfer function will be dimensionless. Now, in the transfer function equation we assume that Xs and Ys are known to us, but sometimes it can happen that you know only Xs and Hs, that means you know only the input voltage and the transfer function of the circuit. In that case you can find the value of Ys, that is output response of the circuit with respect to given input. So, you will say that Ys is nothing but Hs into Xs. Now, you can take the inverse Laplace transform of Ys to get the value of output response of the circuit. As a special case, if we say that xt, that is the input is unit impulse function, we will say that Xs is nothing but equal to 1. In that case, you will say Ys is equal to Hs, and therefore, the inverse Laplace transform at both sides will give you the Yt is equal to Ht. So, Ht is nothing but inverse Laplace of the transfer function. So, this represents unit impulse response of the circuit. So, when it is excited by a unit impulse function, the transfer function will give you the unit impulse response of the circuit. So, we can also say that Ht is nothing but the time domain response of the network when unit impulse is given as an input to the network. Now, as Hs is the Laplace transform of the unit impulse response of the network, once the impulse response Ht of the network is known, that means that we know the response of the circuit when a unit impulse input is provided. then we can obtain the response of the network to any input signal in S domain using convolution integral in time domain or corresponding the S domain analysis for convolution integral. This we will discuss in the next session, where we will see what do you mean by the convolution integral and how it can help in finding out the output response of a circuit where we know the input impulse response of the network. So, this we will analyze when we will discuss about the convolution integral. So, before going into that detail, let us try to understand what are the various approaches to find the output response with the help of transfer functions. So, basically we have two ways to process the information and finding out the output response. So, first method is that let us assume that we have one convenient input access. So, this access can be either unit impulse or maybe unit step function, unit ramp, whatever it is, you can assume a convenient input. Now, you will use the circuit analysis techniques what we discussed in our previous lectures. So, that is like current or voltage division or nodal or mesh analysis. So, you can apply those techniques and find the output y s. Now, when you get the output y s, then you will try to find out the ratio of the two, and when you find out the ratio, that is H s equal to y s upon x s, you know x s, you can apply the circuit analysis and find the output, and then you obtain the ratio of the two to find the transfer function, or if you know the transfer function, you can straight away find the output response of the circuit. Now, another approach which you can follow is called as a ladder method. So, what does ladder method means? Basically, it involves walking through the circuit. In this approach, we assume that output is 1 volt or maybe 1 ampere or as appropriate. So, the difference between first approach and second approach is that in first approach we assume input as known, and we take some assumption that the input given to the circuit is maybe unit step or something like that. But in case of ladder method, we first assume output. So, it means that we will assume say 1 volt or 1 ampere as an output which we have got from the circuit, and then we use the basic laws of Ohm's and Kirchhoff's law. Generally we use only the Kirchhoff current law because it is more convenient in walking through the circuit, and then we obtain the input. It means that what we are doing, we are starting from output and using the circuit, we are trying to find out what would be the corresponding input for the output given to the circuit. So, this we can find out the input, and then you can find out easily the transfer function by giving the value of transfer function would be that y s upon x s. Again here y s would be unit. So, 1 upon x s would be the transfer function for this particular case. So, now these are the two methods, you can use either of them based on your convenience, but this approach, what is the ladder approach we discussed, is more convenient because when the circuit has many loops or nodes, applying nodal or mesh analysis become cumbersome. So, if you see the first case, if you have a complex network where you have multiple mesh and nodes available, then applying the nodal or mesh analysis would be little bit cumbersome. So, that is why compared to first method, second method, that is the ladder method, is more appropriate in case of complex networks. So, we will use this as a convenient method for finding out the transfer function of the network. Now, in the first method, as we discussed, we assumed input and we found the output, while in second method we assume the output and then find the input. Now, in both methods you calculate Hs as the ratio of output to input transform, and we have to keep in mind that these two methods will only be applicable when you have the linear circuit. So, the circuit which follows the linearity property, that circuit can be used to find out the transfer function using either the conventional method where you analyze the circuit with the help of various circuit analysis technique, or you can use the ladder method. So, now to understand the finding out the transfer function, let us take few examples so that you can understand the concept more clearly. Let us take first example. In this case, the output of a linear system is yt, and the yt is given as 10 into e to the power minus t cos 4t ut, and input given is xt is equal to e to the power minus t ut. Now, what we have to do? We have to find the transfer function of the system and its impulse response. So, the transfer function you can find out with the help of the S domain analysis. So, you have to first convert yt into S domain and xt into S domain. So, when you convert yt is equal to 10 e to the power minus t cos 4t ut into S domain, what you will get? 10 will be your instead of S you will put the value as S plus 1. Now, since it is a cos 4t, if you correlate with the transfer function of cos omega t, the transfer function of cos omega t is S upon S square plus omega square. So, we will put cos 4t as S upon S square plus omega square. So, here omega is nothing but 4. So, you get 4 square. Instead of S, what we will write? We will write S plus 1. The ys which you will get from the yt function will be 10 into S plus 1 divided by S plus 1 square plus 4 square. Now, the input function is e to the power minus t ut. The Laplace transform of ut is nothing but 1 by S, since e to the power minus t is attached to the unit step function, and this will become 1 upon S plus 1. Now, since Hs is equal to ys upon xs, you will put ys in numerator and xs in denominator, and when you will simplify you will get the value 10 into S square plus 2s plus 1 upon S square plus 2s plus 17. Now, this particular function which you have got, if you rearrange these terms, you can simply write it as Hs is nothing but 10 minus 40 into 4 upon S plus 1 square plus 4 square. How? If you again simplify, then you will get the same function. So, if you put the value, this will become S plus 1 square plus if you put 10 also, 10 into S plus 1 square plus 160 minus 160 divided by S plus 1 square plus 4 square. So, now if you rearrange, it will become 10 into S plus 1 square upon S plus 1 square plus 4 square, and which is nothing but the our original transfer function. So, it means that you can say that the 10 into s plus 1 square upon s plus 1 square plus 4 square can be arranged in this form. So, when you arrange this in this particular form, what you can say that the inverse Laplace transform of 10 is nothing but 10 multiplied by unit impulse function minus 40 into, since we have a this frequency shift function, that is s plus 1. So, this will become e to the power minus t. Then since if you see this you can say as omega upon s square plus omega square, which is nothing but the inverse Laplace transform of sine of omega t. So, if you put this particular inverse Laplace transform of this particular term, you can simply correlate that omega is nothing but 4. So, you can write sine 4t for this, plus for s plus 1 you will have term added as e to the power minus t. So, finally, what you get is the transfer function h s in this form, and then you can say h t, that is the time domain value of h s, which is nothing but the impulse response of the transfer function, means you can say 10 delta t minus 40 e to the power minus t sin 4t, and then you multiply with unit function to say that this is applicable for time t greater than 0. So, this would be nothing but the unit impulse response of the circuit. So, this will help you to understand how you will find out the transfer function and then the unit impulse response of the system. Now, let us take another example. Here we need to find out the transfer function V naught s upon I naught s for the circuit which is given in the figure. So, in this figure you will see inductor and capacitor both are there, and you have been given the current as I naught. What we have to find out? The ratio between V naught by I naught in S domain, that would be the transfer function for the circuit. Now, if you see this particular circuit, you will see that the I2 value, that is the current I2, can be found with the help of current division method. Now, in case of current division method, how you will apply? You see that the impedance of this particular leg is S plus 4. So, the current flowing in this particular leg would be S plus 4 divided by the impedance of the complete loop. So, that is S plus 4 plus 2 plus 1 upon 2 s, then multiplied by I naught. So, I2, that is the fraction of I naught which is flowing in this leg, would be given by S plus 4 into I naught divided by S plus 6 plus 1 upon 2 s. Now, when you see this current and this current is I2, and when you are asked to find the value of V naught would be nothing but I2 into the 2 ohm resistance. So, you will say that V naught is nothing but 2 into I2. So, you get the value of V naught is nothing but 2 into S plus 1 I naught upon S plus 6 plus 1 upon 2 s. When you will rearrange, you will put I naught in denominator. So, it will become now the transfer function, that is V naught upon I naught in S domain equal to 4 s into S plus 4 upon 2 s square plus 12 s plus 1. So, here in this particular case we used current division method, that is our first method of finding out the transfer function, where we use various circuit analysis techniques. So, with this we get the transfer function of the circuit. Now, next is that let us try to apply ladder method, and we will try to find out the value of transfer function when we apply the ladder method. In case of ladder method, what we assume? we assume output voltage as known. So, what we will do here, we will say that the output voltage given is V naught equal to 1 volt. So, when you say that V naught is 1 volt, the current I 2 which is flowing in this leg will become V naught by 2. So, you will say that it is 1 by 2 ampere. Now, when you know the value of current I 2, you can find out the voltage V 1 which is across this particular leg. So, the voltage across this as well as across this leg will remain same because both are in parallel. So, what we will do, we will find out the value of V 1. So, V 1 we can find in the terms of I 2. So, V 1 is nothing but I 2 into 2 plus 1 upon 2 s. When you will put the value of I 2 is equal to 1 by 2, you will get V 1 is nothing but 4 s plus 1 upon 4 s. Now, this is the same as voltage across S plus 4 impedance. So, what you can do? You can find out the value of current I 1. I 1 would be nothing but V 1 upon S plus 4. V 1 we have got 4 s plus 1 upon 4 s, and then we will divide again by S plus 4 to find out the value of I 1. Now, we have I 1, we have I 2, both are known in terms of the transfer function. So, what we can do? We can find out the value of I naught. I naught now is nothing but I 1 plus I 2. So, I 1 is 4 s plus 1 divided by 4 s into s plus 4 plus 1 by 2. When you will rearrange, you will get 2 s square plus 12 s plus 1 upon 4 s into s plus 4. Now, you have got I naught, V naught you have assumed as 1 volt. So, what you will do? You will find out the value of transfer function H s is nothing but V naught upon I naught, that is 1 upon I naught. So, when you put the value of I naught, you will get the transfer function 4 s into s plus 4 upon 2 s square plus 12 s plus 1, which is same as we got in case of method 1. So, whether you use first method or second method, you will get the same result. So, with this we can close our today's session. In this session we discussed about the transfer function, and we also said that the transfer function will help in identifying the various circuit synthesis properties. So, we will see in next few sessions that how we will apply transfer function method in those cases, and particularly in next session we will first try to understand what do you mean by convolution theorem and convolution integral, so that we can apply both of the techniques to further analyze the circuits. Thank you.